Welcome to the Deep Dive, where we take a stack of sources and really try to pull out the most important nuggets of knowledge for you. So imagine this. You're a policymaker, maybe, or just someone who's really curious, trying to get a real handle on the economy, specifically something as vital as unemployment. You look at the best models, the latest research, the stuff that's supposed to be the bedrock of how we understand things. But what if those very tools, the ones designed to solve these really complex puzzles, what if they're subtly but actually quite profoundly misleading you? What if the shortcuts that economists have relied on for, decades are actually distorting how we see recessions and booms and the real ups and downs of the job market? Today, we're taking a deep dive into a really fascinating paper. It's called Solving the Diamond-Mortensen-Pissarides Model Accurately by Nicholas Petrosik-Nadeau and Lu Zhang. And that isn't just another economics paper presenting new findings. No, this one challenges the very methods that economists use to get to their conclusions. It suggests our understanding of the labor market might be, built on some shaky computational ground.
Our mission today is to unpack their critical insight that an accurate global projection algorithm, we'll get into what that means, is absolutely essential for truly understanding the dynamics of the Diamond-Mortensen-Pissarides model, or the DMP model for short. We'll explore how the traditional, commonly used approximation methods might be systematically underestimating key aspects of the labor market, giving us potentially a skewed picture of economic reality. By the end of this deep dive, you should not only have a better grasp of this foundational economic model, but also really appreciate the profound impact that computational precision has on how we understand real-world stuff like unemployment and economic cycles. Get ready for maybe some aha moments that might make you rethink how economic insights are even generated. So let's start unpacking this. Our journey begins with this model itself, the Diamond-Mortensen-Pissarides, or DMP model. Why is this specific model so fundamental?
Well, the DMP model is, it's really become the dominant framework for understanding the labor market. It fundamentally changed how economists think about the job market. Instead of assuming, jobs and workers just instantly connect perfectly, it introduced this idea of search frictions.
Search friction.
Yeah, basically it acknowledges that it takes time, it takes resources for workers to find jobs, and just as importantly, for firms to fill vacancies. This friction, this whole matching process, it's just a much more realistic picture of what, you and I actually see happening out there.
Right, it's not instantaneous. And this model, it's not exactly new, is it? It has quite a history in macroeconomics.
Oh, absolutely. Its roots go way back to seminal work in the mid-1980s by Peter Diamond, Dale Mortensen, and Christopher Pissarides. Their work was so foundational, actually, that they later got the Nobel Prize in economics for it. So this isn't some, niche academic thing. It really is a bedrock model.
Wow, Nobel Prize level. So it's used pretty widely then.
Incredibly broad applications. It influences how we think about, everything from the ups and downs of business cycles, recessions and booms, to how central banks think about monetary policy. It even stretches into more specialized areas like understanding how economies recover from really big unexpected shocks, sometimes called endogenous disasters. So yeah, its reach is vast.
Okay, so it's foundational, it's widely used, won a Nobel. You'd think it would perfectly explain what we see in the real world.
Yeah.
But that's not quite the story, is it? There's this issue, this unemployment volatility puzzle.
That's a really critical point. If the DMP model is so fundamental, why does it seem to struggle sometimes to perfectly match real-world observations? And that's exactly what the unemployment volatility puzzle gets at. It was famously highlighted by the economist Robert Schirmer back in 2005. He basically argued that the standard baseline DMP model understated the actual volatility, the swings in unemployment that we see in real-world data.
So the model was just too smooth. It wasn't showing big enough jumps and falls in unemployment compared to what actually happens.
Exactly. It didn't seem to generate large enough fluctuations to match the, sometimes really wild swings we experience during economic booms and busts. It was just too stable compared to the real job market.
Okay, so economists see this puzzle. How do they try to bridge that gap? How do they try to make the model match reality better over the years? I imagine there were quite a few attempts to sort of fix this.
Oh, absolutely. It really sparked a lot of creative research, a lot of debate. The economists proposed various tweaks and modifications to the model. Some introduced the idea of sticky wages, suggesting wages don't adjust instantly to economic conditions, which could maybe lead to bigger unemployment swings.
Because people aren't taking pay cuts immediately when things go bad, so firms lay off more people instead.
Sort of, yeah. Or wages don't rise fast enough in booms, affecting hiring. Others looked at things like fixed matching costs, where firms have this set expense for trying to hire, regardless of how easy or hard it is. And there were also specific calibrations basically arguing that if you plugged in certain specific numbers for the model's parameters, like really small profits for firms and very low bargaining power for workers, then the model could produce more realistic volatility.
So lots of different ideas trying to get the model's output to look more like the real-world data.
Exactly, all aimed at aligning the model with reality.
Okay, and this is where it gets really interesting, right? Because this paper we're looking at by Petrosky-Nadeau and Zhang suggests the problem might not just be the model's assumptions or its calibration numbers, but the method used to actually solve the model in the first place. What's their core revelation here? What's the big insight?
Their key insight, and honestly it feels like a potential game changer, is that a globally accurate algorithm will contrast that with the local ones in a bit, is absolutely critical. It's critical for truly quantifying the equilibrium properties, the outcomes of this DMP model. Basically, how we numerically solve these complex equations can fundamentally change our understanding of the economic reality the model is supposed to describe.
So the math technique matters just as much as the economic theory.
In this case, it seems so. And they hint at really dramatic differences. For instance, they find that log linearization, which is a very, very common local method, might drastically understate the mean and volatility of unemployment.
Understate both how much unemployment fluctuates and its average low.
Yes. And maybe just as importantly, it could also overstate the volatility of labor market tightness. That's kind of how easy it is for firms to hire and overstate the magnitude of the unemployment vacancy correlation.
That correlation is the Beveridge curve, right?
Yeah.
The relationship between job openings and unemployment.
Exactly. So log linearization might be telling us that relationship is much stronger or steeper than it actually is, according to the more accurate solution.
Wow. So it's not just that we might be seeing less volatility than there truly is, but we might also be misinterpreting how tightly linked unemployment and job vacancies are. That's a significant claim. That affects how we interpret economic data, how we think about things like labor market efficiency, and potentially how we design policies.
Precisely. It's like we might have been looking at the economy through a distorted lens without even realizing it. It's a fundamental reevaluation.
Okay, that is a huge claim. It really does sound like we might have been using tools that give us a warped view. Let's dig into these tools more. What are these traditional shortcuts, these perturbation methods that the paper criticizes? Let's start with the most common one, log linearization.
Okay, right. So the traditional shortcuts are generally called perturbation methods, and they're popular mainly because they offer, well, computational simplicity and speed. They're easier and faster to run. The most common one by far is log linearization, which is technically a first-order perturbation. What it does, essentially, is it linearizes the model's equations, which are inherently nonlinear and complex, around a single point, the deterministic steady state.
The steady state being like the long-run average equilibrium point of the economy.
Exactly. Imagine trying to understand a complex, winding road. Log linearization just draws a straight line that's tangent to the road at one specific spot, that steady state point.
So I used this analogy earlier. It's like using a flat map to navigate a small local area. It works okay for short distances right around that known point you started from. But if you try to go far away or understand the whole curved Earth, that flat map introduces pretty significant distortion, right?
That's an excellent analogy. Yeah. For small wiggles around a known, stable economic state, log linearization can be quite useful and computationally cheap. However, the paper also points out that it's, common practice when using these methods to ignore certain constraints. Like the simple fact that job vacancies can't actually be negative. You can't have negative job openings.
You just stop posting jobs.
Right. But log linearization might, in its math, allow for that possibility if the shock is big enough, because it's just following that straight line. This simplification further adds to the potential for error when the economy moves into more extreme states, far from that average point.
Okay, so that's the basic straight line method. Then there's a slightly more advanced version, second-order perturbation. Does that try to capture some of the curve?
It does. The second-order perturbation is a step up in complexity. It tries to improve accuracy by taking into account some of the curvature of the model's equations. So yes, think of it as drawing a slightly curved line instead of a perfectly straight one. It includes second-order terms in its approximation.
So intuitively, that sounds like it should be better, right? More accurate.
You'd think so, but what's really striking, and maybe counterintuitive, is that the paper shows that while it attempts to improve on log linearization, it often introduces even larger errors,
Larger errors.
especially when the economy moves far away from that steady state point. So the illusion of improvement by adding that bit of curvature locally can actually be quite misleading. It can lead to even wilder inaccuracies than the simpler straight line method when you get into deep recessions or big booms.
Wow. Okay. And just for context, how do economists typically run these calculations? Are there specific software tools they use?
Yeah, for sure. Most of these perturbation methods, both first and second order, are implemented using widely adopted software packages. Probably the most famous one is Dynair. Dynair is incredibly popular. It's used in tons of influential empirical macro research, like studies by Cristiano, Eichenbaum, and Evans, or Smets and Wouters. Its prevalence really underscores just how embedded these perturbation methods are in the field.
Which makes this paper's findings even more significant if the standard toolkit might be flawed.
Exactly.
So if these traditional methods, these shortcuts, are prone to potentially large errors, what's the alternative? This is where the paper champions its precision tool. Global projection algorithms, how are these different?
Right. So if perturbation methods are like your flat map, useful locally, then global projection algorithms are indeed the sophisticated, detailed 3D globe. They were pioneered by economist Kenneth Judd back in the early 90s. And the key difference is these methods solve for the model's policy, functions the rules for how agents behave over the entire state space, not just around that single steady state point.
The entire state space, meaning all possible combinations of, say, productivity levels and existing employment levels.
Pretty much, yeah. The whole range of possible economic situations the model can represent. This means they capture the full spectrum, from severe recessions to roaring booms, not just those scenarios that are close to some long-run average.
That sounds incredibly powerful, especially given what you said about the real world having these strong nonlinearities. How do these algorithms handle things like those kinks we mentioned, like when vacancies hit zero? Perturbation methods seem to smooth those over.
Yeah, real-world economic dynamics, especially in labor markets, they're rarely perfectly smooth or linear. Things often hit boundaries, or their behavior changes quite drastically at certain thresholds, exactly like that non-negativity constraint on vacancies. You hit zero, you stop. The paper notes that these projection algorithms are specifically designed to fully capture these nonlinear dynamics and handle these kinked functions correctly.
How do they do that mathematically? Approximating a kink seems tricky.
Well, the authors use a pretty clever approach, building on work by Cristiano and Fisher. Instead of trying to directly approximate the kinked function itself, which is difficult, they incorporate these occasionally binding constraints by carefully approximating conditional expectations around them. Then they derive the policy functions and something called multiplier functions from that. It sort of sidesteps the problem of directly dealing with the kink, avoiding the errors that would introduce.
Okay, that sounds computationally intensive. What specific techniques are the authors using to actually do this projection and ensure the accuracy they claim?
They really employ some advanced computational methods. The paper explores both discrete and continuous ways of representing the state space. For efficiency, they often discretize log productivity, meaning they turn that continuous variable into a series of distinct steps on a grid.
Like approximating a smooth ramp with a set of stairs.
Kind of, yeah. But importantly, they emphasize their preference for a specific method for doing this discretization for persistent processes like productivity, the Rowan-Horst method from 1995. They argue it delivers more accurate results than the perhaps more popular Tauchen method from 1986.
So even the way you build the stairs matters.
It really seems to. And for approximating things in a continuous state space or calculating those conditional expectations accurately, they use sophisticated techniques like Chebyshev polynomials and Gauss-Hermite quadrature.
Okay, those sound complicated.
They are. Think of them as advanced mathematical tools for drawing very complex curves very accurately, or for calculating areas under those curves precisely. It's like using super fine brushes and detailed grids to capture every nuance rather than just sketching a rough outline.
It really showcases a commitment to getting the computation right, doesn't it? It highlights that these subtle choices in numerical methods can actually have really substantial impacts on the final economic conclusion.
Absolutely. It's not just about the economics. It's about the math and the computation, too.
Okay, so we have this foundational DMP model, and we have these two very different ways of solving it. The local shortcuts like log linearization and these complex global projection methods. Let's dive into the first case study the paper uses to show the difference, the Hagedorn-Minovsky, or HM, model from 2008. What's the deal with this specific model?
Right, the HM model. It's a relatively stylized, you could say, simpler version of the DMP, which makes it useful as a starting point because it's easier to analyze. It assumes things like risk-neutral households, meaning they don't care about uncertainty, linear production, and importantly, it assumes that labor productivity is the only state variable driving the economy's fluctuations.
So simpler, just focused on productivity shocks. And Hagedorn and Minovsky, they made a big claim with this model, right, about the volatility puzzle.
They did. They famously argued that their specific calibration, their choice of parameter values for the model, could produce realistic labor market volatilities. Basically, they claimed they could solve Scheimer's puzzle without needing big changes to the DMP model itself, just by choosing the right numbers.
So they thought the basic DMP structure was fine, you just needed to plug in, say, low worker bargaining power or something like that.
Essentially, yes. They argued that with parameters implying a very low value of non-work for workers and thus small gains from matching, the model naturally generated high volatility. They mentioned specific values for things like the time discount factor, how much we value the future, the persistence of productivity shocks, the worker's bargaining weight, the job separation rate, and the elasticity of the matching function, how efficient matching is.
Okay, they have their model, their parameters, their claim of realistic volatility. And this is where Petrossi-Nadeau and Zhang come in with their accurate global solution and start to, well, poke holes in it.
Yeah.
The discrepancies become clear.
This is exactly where the accurate solution starts to reveal some really stark differences. Let's look right at the headline number. Unemployment volatility. HM's original 2008 paper reported a volatility figure of 0.145. They claimed this was close enough to real-world data. Log linearization, applied to their model, actually yields an even lower figure, 0.133.
Okay, so both around 0.13-0.15. What does the accurate projection algorithm find?
The projection algorithm, solving the same model with the same parameters accurately, reveals an unemployment volatility of 0.258.
0.258. That's almost twice as large as what log linearization suggests.
Exactly. It's almost twice as large as log linearization and also significantly higher, about 60% higher than what even the second-order perturbation method gets, which was 0.164.
That completely changes the picture of labor market stability painted by that model, doesn't it? It means unemployment in that calibrated model is far more volatile than HM or the standard approximation methods suggested.
It really does. It fundamentally alters the conclusion about whether that calibration solved the puzzle.
Wow. Okay, so that's the swings, the volatility. What about just the average level of unemployment over time? Does that also show a big difference?
It does. Another major difference. The stochastic mean unemployment rate, that's the average unemployment projection method, is 6.17%.
6.17%. How does that compare to the standard method?
Well, the deterministic steady-state unemployment rate, the single point around which log linearization approximates, is only 5.28%.
So the accurate average is almost a full percentage point higher, 6.17% versus 5.28%.
Yes, almost 1 percentage point higher. This shows that the local methods don't just miss the size of the fluctuations, they also systematically underestimate the average level of unemployment the model predicts over time. That's a pretty big deal for policy discussions about what a normal unemployment rate is.
Definitely. And the Beveridge curve relationship, that unemployment-vacancy correlation, is that also misinterpreted by the local methods?
Yes, that's significantly affected too. Log linearization produces a strong negative correlation of negative 0.848. That implies a very steep Beveridge curve. Vacancies fall a bit, unemployment shoots up a lot, and vice versa.
A tight relationship.
Right. But the projection algorithm finds a correlation of only negative 0.567. That's substantially lower in magnitude.
So the true Beveridge curve in this model is flatter. The link isn't as tight as log linearization suggests.
Exactly. It suggests the labor market, according to this model solved accurately, might be less responsive in terms of how unemployment reacts to changes in vacancies than those local methods led us to believe.
And what about market tightness volatility? How quickly firms adjust hiring efforts?
Log linearization actually overstates that compared to projection. It predicts more volatility in market tightness, 0.327, than the projection method, 0.267. So the local methods might exaggerate how responsive firms are to changing hiring conditions.
So putting this all together, lower average unemployment, lower volatility, a steeper Beveridge curve, higher tightness volatility, the picture from log linearization looks quite different from the accurate solution. What conclusion do the authors draw from this about the HM model and past research?
Well, they state it pretty directly. They say these results cast doubt on the validity of calibration that relies exclusively on steady-state relations, as well as log linearization as a solution method for the DMP model.
It's a direct challenge. They're saying you can't just calibrate to the steady state and then use log linearization to understand the dynamics, because you'll get the wrong answers.
Precisely. The method used to solve the model is just as crucial as the model itself or the parameters you plug in.
Okay, this is really compelling. So why? Why do these two approaches, the local straight curve line versus the global 3D map, give such dramatically different answers for the same model? What's the core economic mechanism driving these nonlinearities that log linearization misses?
Right, the why is crucial. The crux of the difference, the paper argues, lies in the strong, nonlinear dynamics of unemployment within the DMP model. And this nonlinearity stems primarily from those matching frictions we talked about earlier. These frictions induce something economists call a congestion externality. Think of it like traffic jams in the labor market. The effect isn't the same when there are few cars versus many cars.
Okay, congestion. How does that play out differently in recessions versus booms? Why is it asymmetrical?
Let's take recessions first. In a recession, you have lots of unemployed workers competing for a relatively small pool of vacancies. It's like rush hour with only one lane open. This intense competition means the vacancy filling rate, how quickly firms fill their open jobs, gets really high. It approaches one. It becomes very easy for a firm to fill a posted vacancy.
Because there are so many applicants for each job.
Exactly. But this means that the marginal cost of hiring hardly goes down, even if the firm's profits are falling, because filling the next vacancy is still pretty easy. This situation exacerbates the impact of falling profits to stifle job creation. Firms don't get much cost relief on hiring, profits are down, so they just stop creating jobs. And this causes unemployment to spike up rapidly.
Okay, so a bottleneck in hiring cost reduction makes unemployment surge in bad times. What about booms? Is it just the mirror image?
Not quite a perfect mirror image, that's the asymmetry. In booms, you have the opposite situation. Many vacancies competing for a small pool of unemployed workers. Now the firms are the ones facing congestion. Here, the vacancy fill rate becomes very sensitive to an extra vacancy. Adding one more job posting makes it significantly harder to fill any of them because the pool of available workers is so small.
So hiring costs shoot up quickly.
Exactly. Marginal hiring costs rise rapidly, and this slows down job creation. Even though times are good, firms become hesitant to post too many vacancies because it's just so costly and difficult to fill them. So unemployment falls, and market tightness, vacancies relative to unemployment, rises, but it happens only gradually. The expansion is sort of self-limiting due to this hiring congestion.
And log linearization, being just a straight line approximation around the average, completely misses this difference between the rapid spikes in recessions and the gradual falls in booms.
Precisely. It smooths over these sharp asymmetrical dynamics. It can't capture that kind of state-dependent behavior very well.
The paper uses a simulation to illustrate this, right? Figure 2 shows sample paths. Can you paint a picture of just how different those paths look?
Yeah, the visual difference is really striking. They simulate the model using both methods, feeding them the same series of underlying productivity shocks. The unemployment rate generated by the projection algorithm shows these dramatic spikes. It can shoot up to more than 10% relatively frequently, and in really bad simulated recessions, it hits almost 29%.
29% unemployment in the model.
Wow.
Yeah.
Whereas the path generated by log linearization, it's much smoother. No such spikes are visible. In that same deep downturn where projection hit 29%, log linearization only showed unemployment reaching about 9%.
A massive difference in the perceived severity of a downturn. What about the booms?
Conversely, in booms, the projection path shows unemployment bottoming out around 3.44%. Log linearization predicts an even lower unemployment rate, down to 1.47%. So it implies a stronger, faster recovery than the accurate model suggests.
And market tightness during those booms. Does log linearization get that right?
No, that's also way off. In boom periods, the market tightness predicted by projection is often much lower than what log linearization predicts. In one specific example they highlight, projections tightness was only about 40% of log linearization's value.
Why is that?
It goes back to that congestion. Log linearization underestimates the congestion externality in booms. It doesn't fully capture how hard it gets for firms to find workers when unemployment is low. This leads it to predict an overly optimistic view of how easily firms can hire and expand in good times.
Okay, so the individual paths look totally different. This must mean the long-run pattern, the overall distribution of unemployment, is also completely different between the two methods, right? The ergodic distribution, as paper calls it.
Absolutely. If the short-run dynamics are so nonlinear and asymmetric, it fundamentally changes the long-run picture of the economy. The projection algorithm reveals a relationship between unemployment and productivity that is highly nonlinear. When productivity is low, recession, unemployment spikes drastically. They mentioned it can reach over 65% in some extreme simulations.
65%.
In the simulations, yes. But when productivity is high, boom, unemployment falls only gradually. This asymmetry leads to an overall unemployment series that is positively skewed with a long right tail.
Meaning you have a higher chance of really bad unemployment outcomes than really good ones.
Sort of, yeah. It means those extreme recessionary spikes pull the average up. The mean unemployment rate, around 6.2%, ends up being much higher than the median, around 5.4%, reflecting the influence of those severe downturns. And the gap between the best case 2.5 percentile and worst case 97.5 percentile unemployment rates is significantly wider than what log linearization shows.
And how does log linearization's long-run view compare? I'm guessing much more symmetrical.
Exactly. In stark contrast, log linearization shows a relationship between unemployment and productivity that is virtually linear. The correlation is almost perfectly negative, MIC is 0.96. The maximum unemployment it ever predicts in its simulations is only around 10%, dramatically lower than the 65% plus sometimes seen with projection. Its simulated unemployment series is largely symmetric. The mean and median are almost identical, both around 5.3%, and the skewness and kurtosis, measures of asymmetry and fat tails, are near zero.
So log linearization paints a picture of a much more stable, predictable, well-behaved labor market. It systematically misses the possibility of those severe high unemployment events captured by the global algorithm.
It's almost like looking at two completely different economies generated by the same underlying model, just solved differently.
That's a profound difference. The paper also digs into nonlinear impulse responses. These show how the economy reacts to a sudden shock, like a hit to productivity. How do these responses further highlight the nonlinearity missed by log linearization?
This is really fascinating because it lets us see the asymmetry in action dynamically. The key finding is that the projection-based responses, especially for unemployment, are substantially stronger in recessions than in booms.
So the same size shock has a bigger impact when the economy is already doing poorly.
Precisely. For example, they look at a negative 1 standard deviation productivity shock. In a bad economy, simulated to be at the 5th percentile of the productivity distribution, projection shows unemployment shooting up by 0.85 percentage points on impact.
Okay, a significant jump. What about in a good economy?
In a good economy, at the 95th percentile, that same negative shock causes unemployment to rise by only 0.08 percentage points according to projection. That's more than 10 times smaller.
Wow, an order of magnitude difference in the response depending on the state of the economy. How does log linearization handle this?
It completely misses this state dependency. Log linearization predicts an unemployment response of about 0.15% or 0.16%, regardless of whether the economy is good or bad. So it drastically understates the impact of a negative shock in a bad economy, predicting 0.15% when projection shows 0.85%, and actually overstates the impact in a good economy, predicting 0.16% when projection shows only 0.08%.
Gets both the magnitude and the asymmetry wrong. Does this state-dependent response apply to other variables too, like market tightness or wages?
Yes, it does. For market tightness, log linearization often overstates how much it falls in response to a negative shock, especially in good economies. Again, it fails to capture the true gradual nature of expansions and the impact of congestion. And for wages, the projection solution reveals them to be quite inertial, especially in downturns. Wages drop less in response to a negative shock when the economy is already bad compared to when it's good. Log linearization also misrepresents this dynamic.
So the entire dynamic fabric of the labor market job finding, firm hiring behavior, wage setting, behaves nonlinearly, and log linearization misses it.
That seems to be the core message for the HN model, yes.
Okay, this all comes down to accuracy then. The paper isn't just showing these differences exist, it's arguing the projection method is right and the others are wrong. How do they actually quantify the errors to prove this?
Right, because just showing different results isn't enough. You need to show one is actually closer to the true solution of the model's equations. The gold standard for measuring this computational accuracy is using Euler equation errors, a concept really formalized by Ken Judd back in 1992.
Euler equations. Those represent optimal choices, right?
Exactly. Think of it like this. In a correctly solved economic model, individuals and firms should always be making the best possible decision today, given their rational expectations about the future. The Euler equations mathematically represent these optimal decision rules, like how much to invest or whether to post a vacancy. So the Euler equation errors measure how much the numerical solution you've calculated deviates from satisfying those optimal conditions, point by point, across the entire economic landscape, the state space.
And in a perfectly accurate solution, these errors should be
0. Or, in practice, extremely close to 0, like within the limits of computer precision.
Okay, so when they calculate these errors for the HM model,
Right.
what does it show about the projection algorithm's accuracy?
The results are really impressive for the projection method. The errors are extremely small. They're typically in the magnitude of 10 to the minus 4. If you look at simulations, the mean error is incredibly tiny, like 2.22 times 10 to the minus 6. The mean absolute error is also minuscule, around 6.84 times 10 to the minus 6. And even the maximum absolute error found anywhere is only 1.5 times 10 to the minus 4.
So incredibly precise. The projection method is faithfully solving the model's underlying optimality conditions.
That's what the evidence strongly suggests.
How do the local perturbation methods log linearization and second order stack up against this accuracy benchmark? I have a feeling it's not going to be pretty.
You're right, the contrast is quite stark. The Euler errors for log linearization are 3 to 4 orders of magnitudes larger than those from the projection method.
Orders of magnitude, like thousands of times larger.
Yes. The errors can vary dramatically depending on where you are in the state space, ranging from about negative 11.5% to positive 7.13%. The mean absolute error for log linearization is a significant 3.75%. That's not a small numerical discrepancy. That's an economically meaningful error in the decision rules.
And the second order perturbation, the one that was supposed to be more accurate.
That's maybe the most concerning finding. The second-order method can be even less accurate. Its errors range even more widely, from about negative 13.9% to positive 13.3%.
Wow. Why is it worse?
It seems particularly inaccurate when the economy moves away from that central steady state point, which is precisely where those nonlinearities really bite. The local curvature it tries to capture just isn't representative of the true global picture far away from the approximation point.
So the shortcuts aren't just less precise. They can be profoundly misleading about whether agents are behaving optimally in the model.
That appears to be the case, based on these Euler error calculations.
That's compelling. But you mentioned earlier that even within global projection methods, the specific technique used to approximate continuous variables like productivity matters. The paper compares Ruwenhorst versus Tauchen for creating those stairs or Markov chains. What did they find there?
Yes, this is a really important technical point, a nuance that often gets overlooked but can have a surprisingly large impact on the results. They specifically contrast the Ruwenhorst method from 1995 and the more commonly used Tauchen method from 1986 for discretizing that persistent productivity process.
And the verdict? Which one performed better?
Their findings strongly favor the Ruwenhorst method in this context.
What makes Ruwenhorst more robust or superior here?
Well, firstly, the results obtained using Ruwenhorst discretization are shown to be very close to the results from using a fully continuous state space method, which is like the ultimate benchmark for accuracy. For example, the unemployment volatility calculated using Ruwenhorst was 0.257 compared to 0.259 with the continuous method practically identical. Crucially, it's also robust to the number of grid points, the number of stairs you use. Using 13 points gave very similar results to using 17 points, and even using just 5 points wasn't wildly off. This consistency is really valuable.
So it gives reliable answers even if you simplify the grid a bit to save computation time.
It seems much more stable in that regard, yes. And its Euler residuals remain fairly accurate even with fewer grid points.
Okay, Ruwenhorst sounds good. What about the more popular Tauchen method? How did it fare?
Unfortunately, the Tauchen method proved to be quite sensitive to the range of the grid chosen. This is a known issue, especially for highly persistent processes like productivity in these models. If they used a smaller grid range, similar to what HM might have used in their original work, the Tauchen method gave an unemployment volatility of only 0.154, but using Tauchen with a larger, more appropriate grid range yielded 0.299, a huge difference. and still different from the Ruwenhorst continuous benchmark of around 0.258.
So the results jump around depending on how you set up the grid with Taucan.
Exactly. This sensitivity casts doubt on the Taucan method for these kinds of highly persistent processes. The Euler residuals calculated using Taucan also confirm this, showing much larger errors, sometimes an order of magnitude larger than Ruwenhorst's, especially if the grid range isn't chosen carefully.
So the takeaway is that for these kinds of models, Ruwenhorst seems to be the more reliable discretization choice.
That's certainly the strong implication from this paper's analysis. It reinforces the idea that precision matters down to the level of these specific computational choices.
Okay, given how much the solution method impacted our understanding of the relatively simple HM model, let's move to the second case study, the Petroskino-Zankun, or PZK, model from 2015. This sounds like a much richer, more complex attempt to capture reality.
It is indeed. The PZK model takes several steps beyond the simpler HM model. It incorporates risk aversion, meaning households in the model dislike uncertainty and try to smooth consumption. It also features nonlinear production with capital.
So it's not just labor and productivity, but capital investment decisions are also part of the story now?
Exactly. And because of this, the PZK model has 3 state variables that determine the economy's position: the level of employment, HMNT, the stock of capital, KT, and the level of log productivity. This makes it much more realistic, capturing interactions between labor and capital markets.
But also much harder to solve, I imagine.
Absolutely. Far more challenging to solve accurately because of that higher dimensionality.
What kind of extra complexity does this richer structure introduce into the actual equations that need solving?
Well, you now have 2 key intertemporal optimality conditions that need to hold simultaneously. There's still an intertemporal job creation condition, similar to the HM model, dictating firms' hiring decisions over time. But now there's also an investment Euler equation, which guides firms' optimal capital investment decisions.
So firms are choosing both how many workers to hire and how much equipment to buy, considering the future.
Precisely. It's a more integrated decision process. Interestingly, one thing that simplifies slightly is that, unlike in the HM model, the constraint that vacancies can't be negative is never binding in their simulations of the PZK model.
Why not?
Because the presence of capital acts as a buffer. Firms can adjust investment margins, which prevents the desired level of vacancies from ever hitting zero, even in quite severe downturns in their setup.
Okay, 3 state variables: employment, capital, productivity. That sounds like a recipe for the curse of dimensionality that plagues these kinds of dynamic models. What level of computational power is needed to solve this beast accurately using projection methods?
You've hit the nail on the head. The 3-dimensional state space makes the computation incredibly demanding. The authors have to employ very sophisticated techniques, specifically a finite element method with cubic splines. They use a grid with 100 nodes, or points, for employment, and another 100 nodes for capital, and they have to solve this for each of the 17 grid points they use for productivity, using the Ruwenhorst method, by the way.
100 times 17. That's a lot of points to calculate.
It is. It means they are simultaneously solving a system of 340,000 nonlinear equations to find the equilibrium policy functions across this entire 3-dimensional grid. This is not something you can do on your laptop over a coffee break.
340,000 nonlinear equations. Seriously, how long does that take to run?
The computational cost is immense. They report it took a bit more than 6 days to converge on a Dell workstation with 32 3.1 gigahertz CPUs and 384 gigabytes of physical memory.
6 days on what sounds like a supercomputer. Okay, that really underscores why economists might be tempted by those faster, simpler approximations like log linearization. Even if they are less accurate, the trade-off is stark.
Absolutely. The computational burden of achieving this level of global precision, especially in higher dimensional models, is enormous. It's a major practical constraint.
So given this complexity, how did they calibrate the PZK model? How did they choose the parameter values to make it comparable to the real world?
They adopted what they call a common practice in the business cycle literature. They calibrated the model by matching its log linear moments to key statistics from post-war U.S. data, specifically from 1951 to 2014.
Wait, they calibrated it using the log linear moments, even though they argue log linearization is inaccurate.
Yes, and that's a crucial part of their strategy. They essentially set up the model so that if you were to solve it using log linearization, it would match certain features of the U.S. economy, like the volatility of output growth, consumption growth, etc. They use standard data sources like NIPA and BLS, plus a help-wanted index for vacancies.
So they deliberately made the log linear version look right, according to standard practice. which then allows them to show how much the accurate projection solution deviates from that familiar but potentially misleading benchmark.
Exactly. It's a clever way to highlight the quantitative difference the solution method makes, starting from a baseline that other researchers would recognize.
Brilliant. Okay, so after all that computational heavy lifting, 6 days of number crunching, how does the projection algorithm's view of the economy, specifically business cycle and labor market moments, differ from what log linearization tells us in this richer, calibrated PZK model?
The differences are again profound and largely consistent with what we saw in the simpler HM model, but perhaps even more pronounced here. Let's look at the main business cycle moments. First, things like output growth. Projection consistently yields higher volatilities for all the key growth rates compared to the log linear solution it was calibrated to match.
Higher volatility even though it was calibrated to match the log linear volatility.
Yes. For example, output growth volatility is 3.26% with projection compared to the 1.72% target from log linearization, nearly double. Consumption growth volatility is also higher, 2.60% versus 2.41%, and investment growth volatility is significantly higher, 4.45% to 3.26%.
So even when calibrated to match log linear results, the true nonlinear dynamics of the model generate substantially more volatility in the main economic aggregates. Log linearization systematically understates the economy's overall variability.
That's what these results strongly suggest. Interestingly, the autocorrelations measures of how persistent cycles are largely comparable across the two methods. So the persistence might be captured similarly, but the magnitude of the fluctuations is significantly underestimated by log linearization.
Okay, that's the broader business cycle.
Yeah.
What about the labor market moments? These are central to the DMP framework, so the differences here must be critical.
They are, and they are even more striking. Let's start with the average unemployment rate. Log linearization, by construction from the calibration, gives a mean unemployment rate around 5.75%.
Okay, a typical historical average for the U.S. What does the accurate projection method find?
The projection algorithm yields a mean unemployment rate of 10.75%.
10.75%. That's nearly double the log linear rate.
Yes. The paper states the log linear mean is only about 1/2 of the projection mean. This is a massive difference. It suggests that the accurate model, capturing the nonlinearities, predicts a substantially higher average level of unemployment over the long run than standard methods would indicate.
That has huge implications for how we think about full employment or the natural rate of unemployment. What about volatility?
Similar story to the HM model, but maybe less dramatic here. Log linearization, 0.133, still understates unemployment volatility compared to projection, 0.158.
And market tightness volatility.
Log linearization, 0.355, overstates it compared to projection, 0.254. So again, it suggests firms are more jumpy in their hiring adjustments than the accurate model implies.
And the Beveridge curve, the unemployment vacancy correlation.
Log linearization, note of 0.536, again, overstates the magnitude compared to projection, note of 0.359. It shows a steeper curve than the accurate solution suggests.
So the patterns are consistent. Log linearization underestimates mean unemployment and its volatility, but overestimates tightness volatility and the UV correlation magnitude. Are there other interesting differences maybe in how unemployment relates to productivity?
Yes, that's another critical point highlighted for the PZK model. Log linearization shows a very strong negative correlation between unemployment and labor productivity, note of 0.881.
Meaning when productivity goes up, unemployment goes down very reliably in the log linear world.
Right, but this correlation is substantially higher in magnitude than what you see in the actual U.S. data, which is only note of 0.158, and also much higher than what the projection method finds, note of 0.337.
So log linearization makes the labor market seem far too sensitive to productivity shocks compared to both reality and the accurate model solution.
That's the implication. It suggests these log linear models might lead us to believe that productivity changes have a much greater, more direct, and more immediate impact on unemployment than they actually do, or than the more accurate nonlinear model suggests.
Okay, these are significant differences in the basic statistics of the model. I'm guessing these translate into very different dynamic behaviors as well, like those nonlinear impulse responses we discussed for the HM model.
Absolutely. The richer PZK model, when solved accurately, exhibits even more pronounced nonlinear dynamics. The projection solution again shows strong nonlinearity, particularly with unemployment spiking much more dramatically in recessions.
Driven by those same factors, congestion and wage inertia.
Yes, the paper attributes it to the persistent congestion externality and wage inertia, which combine to make unemployment shoot up sharply when negative shocks hit. And just like before, log linearization misses it almost entirely, predicting a much smoother, less volatile path for unemployment.
Same story in recessions. What about market tightness during booms in the PZK model?
Again, log linearization understates the congestion externality during booms, because it doesn't fully capture how difficult hiring becomes when unemployment is low. It tends to predict excessively low unemployment and excessively high vacancy rates and market tightness compared to the more realistic projection solution. It makes the expansionary phase look too easy.
And the impulse responses themselves. Do they confirm that stronger reaction in bad times for the projection method in this more complex model?
They do, very clearly. Looking at unemployment responses to productivity shocks, projection shows reactions that are substantially stronger in the bad economy.
Can you give an example?
For a negative productivity shock, projection shows unemployment jumping by 1.35 percentage points if the economy is already in a bad state. But if the economy is in a good state, the same shock only causes a 0.035 percentage point rise. Again, a huge difference depending on the initial state.
Over a full percentage point difference in the impact of the same shock. How does log linearization compare here?
Log linearization predicts a rise of about 0.33 percentage points in the bad economy. That's less than 25% of the true response shown by projection. It massively underestimates the vulnerability of the labor market during downturns.
And does this pattern of stronger responses in bad times hold for output, consumption, and investment too in the PZK model?
Yes. The projection solutions show that the responses of output, consumption, and investment are all stronger in the bad economy. For example, a positive productivity shock causes output to rise by 2.23% in a bad economy, but only by 0.68% in a good economy, according to projection.
And log linearization.
Log linearization, again, understates the responses significantly in the bad economy. For that output example, it predicts a rise of only 1.17% in the bad economy, just over half, 52.47% of the response shown by projection.
This is really concerning. If policymakers are using models based on log linearization, they might be consistently underestimating how badly the economy will react to negative shocks or how strongly it might respond to positive stimulus, especially when it's already struggling.
That is precisely the kind of implication that this research raises. The quantitative difference in predicted responses is potentially large enough to matter for policy design.
Okay, let's talk accuracy checks again for this complex PZK model. Given the huge computational effort for projection, how do its Euler equation errors look? Are they still acceptably small?
That's the crucial check on whether the complex solution is trustworthy. For the PZK model, the Euler errors are measured slightly differently, as unit-free residuals relative to optimal consumption. For the projection algorithm, the errors are described as mostly acceptable. The maximum absolute error for the job creation condition is 1.5%, and for the investment condition, it's 0.39%.
1.5% doesn't sound as tiny as the errors in the HM model.
It's true, they are larger. The authors acknowledge this and note they'd ideally want the job creation errors in particular to be even smaller. However, they argue it's a practical limitation given the extreme computational intensity of solving those 340,000 nonlinear equations. It represents a trade-off between precision and feasibility, but they are still vastly smaller than the alternative.
Okay, so projection is reasonably accurate, though perhaps not perfect given the complexity. What about log linearization and second-order perturbation for the PZK model? Are the errors still huge?
Oh, yes. For log linearization, the errors are definitively inaccurate. The maximum absolute job creation error is a massive 27.16%.
27% error on the optimal hiring decision. Yikes.
Exactly. And while the investment error for log linearization might appear relatively small, the paper dismisses this as an illusion.
Right.
Why? Because, as shown by simulations, the log linear economy stays within a small neighborhood of the deterministic steady state. It never actually visits the regions where the large nonlinearities and thus large potential errors occur.
So it looks accurate only because it never leaves its comfort zone where the approximation is designed to work.
Precisely. It's like saying the flat map is accurate because you never tried to use it to navigate across the globe.
And the second-order perturbation, does it redeem itself in the PZK model, or is it still problematic?
It's arguably even worse here. The paper describes it as dramatically inaccurate, especially for the job creation condition. The maximum absolute error they report for second-order perturbation is an astonishing 654.6%.
650%. That's not even an error. That's just meaningless, right?
It indicates a complete breakdown of the approximation. The reason becomes clear when you look at simulations generated by the second-order method. The economy often wanders far away from the deterministic steady state, sometimes predicting employment levels plunging to extremely low levels, even lower than projection shows in its disaster states.
And when it gets that far away, the local approximation becomes totally unreliable.
Exactly. The locally calculated coefficients used in the second-order approximation just don't apply anymore in those extreme regions, leading to these wildly inaccurate results.
The paper uses scatter plots, figure 10, to visualize this, right?
Yeah.
Showing where the different solutions explore.
Yes, those plots are very telling. The projection simulations cover a wide range of both employment from 0.225 up to 0.963 and capital from 10 up to 40.45. It really explores the state space, capturing true nonlinear behavior, including potential disaster dynamics where employment is substantially far away from the steady state value.
And the other methods.
Log linearization simulations cover only a small area clustered tightly around the steady state for both employment, 0.839 to 0.99, and capital, 28.9 to 41.5. This visually confirms its inability to capture large deviations. Second-order perturbation, as mentioned, can wander far off, with employment sometimes plunging to 0.03 in its simulations, explaining its wild inaccuracy.
So the perturbation methods just don't capture the true scope of economic possibilities predicted by the model. One final check. How robust are the projection results for this complex PZK model? Do they change much if the authors tweak their computational setup?
That's an important sanity check. The authors show that the projection algorithm's results demonstrate remarkable robustness. They are generally consistent even when changing choices in the grid parameters, like the number of grid points used for employment and capital, or the lower bounds of the grid.
And what about the specific approximation method used within projection, like cubic splines versus Chebyshev polynomials?
They are also robust to the basis and degree of function approximation. Switching between cubic splines and Chebyshev polynomials didn't fundamentally alter the main findings.
So the core results, the higher volatility, the higher mean unemployment, the nonlinear dynamics aren't just artifacts of one specific, potentially fragile computational setup.
That seems to be the case. The key business cycle and labor market moments mostly differ only in the second or third decimal place across these various computational specifications. It lends confidence to the accuracy claim.
Is there any trade-off? Does using, say, a coarser grid affect anything?
There is a slight trade-off. While using smaller grids can still give reasonably accurate moments, like average volatility, they do tend to result in somewhat higher maximum absolute Euler equation errors. This suggests less precision in certain, perhaps less frequently visited parts of the state space. It highlights that balance between computational cost and achieving the absolute highest accuracy everywhere.
Got it. Okay, this has been a truly fascinating and, frankly, quite eye-opening deep dive. Let's try to wrap up and recap the main messages from this Petrosky, Nato, and Zhang paper. What's the absolute core takeaway?
The single biggest message, reiterated throughout the paper, is that an accurate global algorithm is critical for quantitatively assessing the Diamond-Mortensen-Pissarides model. You simply cannot rely on the traditional local approximation methods if you want quantitatively reliable answers.
And specifically, what are the main biases of those traditional methods?
We've seen consistently across both the simple HM and the complex PZK models that log linearization systematically understates the mean and volatility of unemployment. At the same time, it overstates the volatility of labor market tightness and the magnitude of the unemployment-vacancy correlation. It gives a distorted picture of the labor market's key features.
And the second-order perturbation, which intuitively felt like it should be better.
That often turns out to be even worse. It can induce severe Euler equation errors, often significantly larger than those from log linearization, particularly when the economy moves far away from its average state. It's a potentially dangerous illusion of improvement.
The implications of this seem huge for economics. It suggests a lot of previous research might need rethinking.
That's exactly what the authors propose. They explicitly state that many results in the prior quantitative search literature need to be re-examined with a global solution. That's a really profound statement. It implies that a significant body of macroeconomic understanding, particularly concerning the labor market, might be built, at least partly, on computational assumptions that have systematically skewed our view.
Could widely accepted conclusions be built on, as you said earlier, shifting computational sand.
That's the uncomfortable possibility this research raises.
And is this problem likely confined just to the specific models they analyzed, or is it probably a more general issue within the DMP framework?
They argue strongly it's a general issue. They emphasize that the strong nonlinear dynamics they uncovered aren't just quirks of the HM or PZK models. They are likely present in any DMP models that manage to generate realistic levels of unemployment volatility.
Why? What's the common thread?
Because, as other research suggests, all these models achieve higher volatility by effectively diminishing the fundamental surplus from a job match. This inherent feature seems to amplify the nonlinearities. So this includes models that use different mechanisms like sticky wages or fixed matching costs. The computational accuracy issue likely applies to them too.
So the bottom line is really about the fundamental importance of the computational methods themselves. It's not just about the economic theory.
Precisely. This whole deep dive really underscores the extreme importance of accurately accounting for nonlinear dynamics in quantitative macroeconomic studies. It's a stark reminder that it's not enough to have a brilliant economic theory on paper. The tools we use to translate that theory into numbers, into quantifiable predictions and insights, must also be precise and robust.
The computational choice isn't a minor technical detail. It can profoundly shape our understanding of economic reality.
And consequently, the policies we might advocate based on that understanding.
Is this the final word, or do the authors see avenues for future research stemming from this?
It's definitely not the final word. They specifically call for further research to evaluate high-order perturbation methods going beyond second order against these accurate global algorithms, specifically within the DMP context. So the investigation into finding accurate and efficient computational tools is ongoing.
Thank you for joining us on this really illuminating deep dive into what feels like some hidden truths about unemployment models. It's become incredibly clear that the computational choices economists make aren't just technical details. They can profoundly shape our whole understanding of the economy. They can reveal a landscape that's far more volatile, more asymmetric, and frankly, more complex than the standard, smoother picture often portrayed. So it leaves us with a rather provocative thought, doesn't it? If foundational models of our economy, like this DMP model, can be so significantly misinterpreted by the common solution methods we relied on for years, systematically underestimating things like the depth of recessions or the true average unemployment rate. Well, what other puzzles in economics might we be struggling with that aren't really puzzles about the economy itself, but simply artifacts of looking through an inaccurate computational lens? And perhaps more importantly, how might these inaccuracies baked into the models used for forecasting and policy analysis be influencing real-world decisions? Decisions about stimulus packages, about labor market reforms, about central bank actions, all potentially relying on a subtly distorted view of reality. It's definitely a question that challenges us to always look deeper, to question the tools as much as the theories. Until next time, keep diving deep.